This learning program is registered with AIA CES for continuing professional education. As such, it does not include content that may be deemed or construed to be an approval or endorsement by AIA of any material of construction or any method or manner of handling, using, distributing, or dealing in any material or product. AIA continuing education credit for this learning program have been reviewed and approved by AIA CES. Learners must complete the entire learning program to receive continuing education credit. AIA Continuing Education Learning Units earned upon completion of this course will be reported to AIA CES for AIA members. Certificates of completion for both AIA members and non-AIA members are available upon request. Welcome, and thank you for taking the time to join us today and for your interest in our continuing education course. This course has to do with the demountable equipment that enhances the flexibility, safety, ADA compliance, and social distancing capacity of live event venues. My name is Alex McCullum. I'm with Staging Concepts, and today we will be covering how demountable equipment can enhance the flexibility, safety, ADA compliance, and social distancing capacity inside of a venue. As an industry leader, it is our intention to assist you with the basics regarding the importance of these products in your design process, ensuring safety while maintaining design intent and aesthetics required for successful end results. Working together from concept to completion with the brightest and most experienced teams available in a collaborative effort is the key to any project success. With all this in mind, let's begin our journey together, starting with defining the purpose and learning objectives of the course. The purpose of today's presentation is to examine the use of demountable equipment, including platforms, stairs, ramps, railing, and seating, with a focus on application, patron safety, building code requirements, social distancing, and structural design in public spaces. All of these items are critical to your design, and many of your choices will affect project budgets and the future use of a venue. As we progress through this material, we hope that the end result will give you a foundation to begin the design process of incorporating demountable equipment into your projects. At the end of today's program, you will be able to identify applications for demountable platforms and equipment in public spaces, discuss the solutions for patron safety and current trends regarding patron experience and social distancing, apply 2018 IBC code criteria related to demountable platforms to the design of safe systems, identify structural design considerations for demountable equipment in specific field applications, specify demountable equipment that is appropriate for the project goals around safety, budget, and venue flexibility. Section 1, Applications and Components. Demountable equipment can be used for many purposes in any facility. However, the two most common types of facilities where you will find this equipment are sporting arenas and performing arts theaters that require maximum flexibility for the variety of events they host. The first type of facility we will explore is a typical sports arena or football stadium. As you look around the stadium, you can see the areas where demountable equipment could be installed. Most of this equipment is built using standard demountable platforms in different applications, but you will also notice some semi-permanent and architectural applications for this type of equipment as well. In a stadium or arena, demountable platforms can be used to create ADA seating infills and ramps, flexible camera positions, VIP loge box seating areas, event-level seating sections, vomitory spanning sections, and concert and performance staging, all using similar standard components to maximize the flexibility of the equipment being used. Other types of demountable equipment include field stairs and forkable seating systems typically found around the field level of a stadium. In a performing arts center or theater setting, most demountable equipment is found on or near the actual stage area in the form of stage straps, orchestra pit fillers, stage extensions, and band/orchestra risers, ADA infill platforms, movable seating, wagon systems, seating, riser platforms, lighting and sound mix positions are found also away from the stage area. These venues need flexibility in the way that stage and audience areas are arranged related to how the space will be used. For example, different stage and audience configurations are needed for different types of performances. Movable, unitized sections with height adjustability can provide that type of flexibility. Some additional applications where you can find demountable equipment would include pool covers, choir risers at worship facilities, and for various uses for corporate events. What is showcased here in the photo on the lower right-hand side of the page is a boat trade show where the flooring of the various exhibits was raised so patrons could gain better access and views inside of the boats being showcased, essentially creating docks all around the trade show floor. So how is that flexibility achieved? Now that you have seen some of the applications where you would use demountable equipment, let us talk about the components that make up most of these installations. The components that you'll kind of see here will typically revolve around the platforms, supports, stair units, guardrails, equipment accessories, as well as ADA systems. The demountable platform is the most important building block in developing flexible spaces. Typical construction is a plywood deck with an aluminum skin backer, which provides a Class A fire rating for the entire platform. The platforms have a locking systems that creates a single monolithic surface when engaged. We'll discuss the engineering of the platforms in later slides, but they are typically engineered to adequately support code and required loads, and higher load capacities or stringent deflection requirements can be met by adding additional structural members. A lightweight frame is important to keep the platforms manageable. Facility staff members typically set up and strike the equipment, so they are typically constructed to be easily be moved by 2 workers. Platforms are also very easy to customize for size and structural capacity, as noted previously, and finish, paint, carpet, or any finished surface materials such as a hardwood or tile or paint can be applied to the plywood. This isometric image shows a typical platform stack-up including an optional added support beam and acoustical insulation. For outdoor applications, polymer or fiberglass panels, aluminum planks, or wood plastic composite decking materials can be used to provide weather resistance. Here's an example of an aluminum plank used in a demountable platform. At a cost slightly higher than the interior plywood counterparts, they provide a system that provides long-term resistance to weather. There are different styles of supports for demountable platforms, and they are chosen based on the application and usage of the system. The typical options you will find include standard legging systems, bridging support systems where structure lies beneath every other platform, beam and column systems typically used where the space underneath the platforms must be available, forkable systems, and rolling systems. Again, system selection should be based on multiple factors, including but not limited to the use, storage, cost, and setup size. Successful project execution starts early in the project lifecycle with contacting a demountable supplier and discussing these factors. Now we'll briefly discuss some of the more common support systems in a bit more detail. Standard legs and cross bracing are by far the most common style of support. It offers the lowest upfront cost, highest flexibility depending on height, smallest storage footprint, and note, you can see here in the slide that legs are able to store inside of the platform cavity either loosely or in flashlight clips when platforms are stacked on carts. Standard legs are offered in either fixed or adjustable height range, but require bracing once you reach heights in excess of 30 inches in elevation. Note the photo here on the slide. Standard legging is great for stadium overbuilds when spanning platforms over an existing concrete tiered bowl to create an ADA or camera platform around the concourse of a stadium. They also work great in theaters for flexible seating configurations below 30 inches in elevation for their ease of use and quick setup and strike times at lower elevations for smaller spaces. Bridge support systems are used frequently for larger setups at taller elevations that need a faster setup and strike times. These types of systems bridge platforms from front to back, left to right, between the support frames, eliminating additional understructure and opening up space underneath the demountable equipment to span obstacles, gain access underneath equipment, or to increase storage space underneath when equipment is in place. Because there are less legs dropping to the ground to support the platforms, time to level the system is decreased because there are less supports to level out. This can be a huge advantage to an installation team that has a larger setup to do in a shorter transition period between events being hosted in the facility. Bridging supports are available in both lightweight aluminum and steel options depending on the application where the system will be installed. As you can see in the slide, carts can be designed to hold each style of bridge support to conveniently assist with storage and transportation to ensure fast setup and strike times. We'll touch more on examples of equipment carts here in a few slides. Beam and column systems are used when there is a project need to span greater distances, typically at taller elevations. A beam and column system tends to require the most engineering assistance, as taller systems or longer spans impact how the system needs to be constructed to meet IBC building codes. These are highly customizable systems and are used for both demountable and semi-permanent solutions. You will find this style of support typically around a vomitory area, in an arena, or a stage trap in a theater where a lot of open space is needed underneath, where players and equipment can pass underneath to the field, or where actors and scenery can pass through to the main stage area. Highly customizable, forkable seating systems are meant to yield additional seating capacity for venues without increasing setup difficulty. This product is designed to fit into tight, venue-specific storage areas, but also achieves a sturdy and permanent quality that allows patrons to feel as though they are standing on solid ground. With towers that combine both bridging from left to right and front to back, this caster-mounted product is long-lasting and transportable. Optional accessories include step units, handrails, guardrails, field walls and padding, camera or video platforms, and wind load anchors. Leveling feet ensure that the rise of the product matches the adjacent concrete of the stadia, allowing the riser to adapt to any unique area or space. Typical forkable risers include an aluminum plank top surface and mounted seats. Forkable riser systems are typically compatible with any type of seating chosen for the venue and is highly adaptable to match the look and feel of the space. This type of system usually requires the most upfront design and engineering assistance, as concepts like wind loading, dynamic loading, and storage logistics need to be worked out well ahead of bid day to ensure that the project is costed correctly upfront and that no details are missed that may derail a project budget later in the process. We will touch on those topics a little more later in the presentation. Accessories for demountable equipment are typically attached to the aluminum frames of the platforms, as shown on the lower left section of this slide. The platform frames are extruded aluminum with grooves on the outside to accept most accessories. Accessories include guardrails and drink rails, ornamental or architectural guardrails. These are just a few ideas, but almost any design of guardrail can be either top-mounted or attached to the side extrusion of a demountable platform. Fixed and adjustable stair units. Larger field stairs are used for patron access down to field or arena level for concerts or similar large events. Closure panels and skirting are also common add-ons for demountable applications to cover support systems and act as chair stops on seating risers. Because the equipment is demountable, you need a way to store and transport this equipment when it is not in use. Depending on the type of venue and the storage space available, having the right style of transportation carts is important to be able to navigate the space and carry all the equipment needed. It is important to pre-plan the storage spaces out to make sure the equipment being designed for the venue will ultimately fit into the storage space available. Each cart is designed specifically for high capacity, easy maneuverability, or for a smaller overall storage footprint. Flatbed carts are great for higher capacity per cart needs, and small components like legs can be stored in the cavities between stacked platforms. A vertical style platform cart can be designed to fit through a standard 36-inch wide door and has varying capacities depending on the size cart that can be maneuvered through a building. Stacking carts are great options when a forklift is available, as you can cut the storage footprint in half by stacking these on one another. From there, you can see there are various cart designs for the different accessories and supports, all meant to store equipment as organized and efficient as possible. Wheelchair and equipment ramps can also be built from demountable equipment using the same or similar components previously reviewed. We will get into more detail in a bit for how these can fit into spaces and how to match them up with relevant ADA codes.
Now that we have some understanding of the demountable equipment, let's discuss how a successful project incorporates it. Virtually all project cycles can be broken down into four main processes: planning, design, development, and deployment. Traditionally, the bulk of the planning and design phase is carried out by architects and consultants specializing in conceptualizing the design, creating the drawings and corresponding specifications, and budgeting to ensure the overall project remains viable for the stakeholders. We're going to take a deeper dive into how incorporating a design assist approach into the planning and design phase facilitates successful projects, especially those containing custom aspects. Finding knowledgeable, reliable, and experienced partners is a cornerstone for any successful project. When incorporating custom equipment or applications into a construction project, these partners take on even greater responsibility to ensure the end product matches the design and fits within the planned budget. So identifying and collaborating with these contacts as early in the project cycle as possible is paramount. Budgeting, digital takeoffs, setting expectations of performance as well as scope of work, and design assistance regarding plans, specs, and engineering are crucial aspects of the pre-construction phase. While some of these details can be determined during the bidding process, our experience has shown that this increases the budget and opens up manufacturing and installation phases to a higher degree of risk for miscommunication and potential pitfalls. The key takeaway is that early collaboration with a design team and a strong, experienced partner result in a more successful project, economically and aesthetically, which is illustrated in this slide. The typical project flow is shown in the above chart, with the understanding that each project is unique and can progress differently in terms of responsibilities and processes. With architects and consultants creating the initial design and defining the budget and scope of work considerations, the next step is to partner with a GC or CM to facilitate the bidding process. During the bidding process, the project team vets out and considers the proposals of engineers, manufacturers, and installers to put together a package that hopefully ends in a result that both meets the vision of the designers and fits within the planned budget. The below chart illustrates the design assist approach, especially useful for custom applications. By involving the manufacturer earlier in the design and budgeting process, the stakeholders gain deeper insight into the variables that can affect budget and the potential risks incurred during production or installation caused by the unique design application. Just to be clear, this process does not circumvent the standard bidding process. Although it is true there are certain projects that are awarded directly, bidding still remains a viable option for this design assist approach. By providing upfront engineering, 3D modeling, budgeting, etc., the potential manufacturing partner still benefits by having a clear understanding of scope and expectations and can manage their bid accordingly. The positive results of this approach are clear and can be dramatic in terms of cost and time savings, satisfying general contractor needs and ultimately the end users, while the end result for all parties is that the design intent is more closely met. On the topic of engineering, I'm going to turn this over to our engineering expert so you can get an idea of the technical information that is important to both understand and communicate about early in the design phase to make project process successful.
Thanks for attending today's presentation. I'm Tony Barnes, a professional engineer responsible for structural engineering at Staging Concepts. I'm going to provide an overview of some of the important technical aspects of demountable equipment. I think in many instances, knowledge of the technical details are left up to engineers, but in my experience, all members of strong project teams are able to have some understanding of the technical requirements so that good early design decisions can be made and costly changes don't occur later in the project life cycle. We'll start by discussing code requirements. As you're all aware, the primary purpose of codes is to provide the minimum requirements to adequately safeguard the health, safety, and welfare of building occupants. In this slide, you'll see some of the code associations that are used to guide demountable systems. And primarily in most jurisdictions, the International Building Code is the most widely referenced and determines most aspects of design. Local codes either adopt the IBC outright or produce a document of their own, starting with the IBC as a basis and then adding or subtracting as necessary. Generally, the code requirements for demountable systems are divided into two primary categories: geometric requirements related to egress and structural requirements. In addition, there are some requirements related to fire protection depending on the use of the system. Demountable assemblies can be used for a wide variety of applications such that a variety of code sections needs to be considered. The geometry of a system is primarily dictated by occupancy and the needs of those occupants. Considerations such as sight lines and overall geometry are primarily determined by the design team, while building code requires various configurations of aisles, stairways, ramps, handrails, guards, and doors to ensure that users can safely move about and use the systems. Those geometric requirements are primarily provided in Chapter 10 of IBC, Means of Egress, and are mostly mirrored in ADA standards. In some instances, OSHA requirements may need to be followed, but those requirements are also similar to IBC requirements, or they're unique to items not covered in IBC, such as work platforms and ladders. Structural requirements, which we'll discuss in the coming slides, are primarily provided in Chapter 16 of IBC. Many of the material-specific design requirements are in other standards that are referenced by IBC, such as AISC for aluminum, or the Aluminum Design Manual, ADM, and some others here that are shown at the bottom for wood and for concrete. Note that in all cases, local jurisdictional codes should be consulted, as most have adopted IBC, as we said before, and related codes, but many jurisdictions have amendments that vary from IBC language. And lastly, NFPA and IBC codes should be referenced for fire resistance requirements. We won't be going into a lot of detail in this presentation about those, as suppliers have a wide variety of solutions using different materials to achieve the necessary levels of protection. Those suppliers should be consulted or consult the building code depending on what type of construction you have. So we'll move into some of the technical requirements. Generally speaking, as you're all somewhat familiar with, loading requirements are the forces that are required to be applied to structures. They come from gravity, dead loads or self-weight, such as dead loads or self-weight, human activity that we call live loads, and the environment, such as seismic, wind, snow, or temperature. Live loads almost always determine the construction of demountable systems. Seismic loads can occasionally affect design in high seismic regions such as California, and wind loads are present only on outdoor structures. Temperature loads are caused by expansion or contraction of the system, and they may need to be considered in certain exterior applications. What we'll first discuss is the difference between uniform loads and concentrated or point loads. Uniform loads, as shown in this slide, are applied on an area basis. So you'll see those units in pounds per square foot, typically, sometimes pounds per square inch, usually across the entire surface. So moving on to the next slide here, concentrated loads, conversely, are applied over a discrete area as defined in IBC based on the specific use. The area varies from 2 inches by 2 inches for stairs to 2.5 feet by 2.5 feet for most other areas. Other areas for concentrated loads may be determined from specific equipment component sizes such as support legs or wheels. So now that we have a little background on some of the terminology, let's discuss the requirements prescribed by the code. Live loads are prescribed in Table 1607.1 of IBC. You'll see that most demountable systems fall into categories 4 or 24, and the range is from 60 psf for areas with fixed seating to 150 psf for stages, so a little over twice that for stages. Note that concentrated loads, while not explicitly defined, may also occur for machinery and other equipment and should be discussed early in the design process with the demountable contractor to avoid unforeseen costs later in the project lifecycle. Note also that concentrated loads should not be converted to uniform loads. For example, if we have a 2,000-pound man lift, you cannot divide by the surface area of a platform and compare that to the uniform load rating. The concentrated loads can cause much more acute local stresses and different failure modes. And we'll talk about that a little bit more later. In the above table from ICC 300 that you see in this slide, used to design bleachers, you'll see other required loads specified for treads, handrails, and guards, which are the same as those found in IBC. In addition to vertical loads, ICC 300 does require the application of lateral or sideways loads. All structures require a lateral load carrying or bracing system just to remain upright and stable. So designers should be aware if they are planning to utilize areas below the structures, as bracing will interfere with open spaces. Structural building walls may be used for lateral support in lieu of the bracing. To go into a little detail on this topic, here's the primary methods of resisting lateral loads shown here in Figure 1. Shear walls are relatively large vertical elements that support lateral loads via in-plane shear are common in building construction. The simplest example is framed wood walls in homes, where the shear is carried by the wall sheathing. In larger commercial buildings, they may be present in elevator shafts or stairwells. Something you might be familiar with, moment frames and brace frames. They're more commonly used in demountable equipment design. The latter, brace frames being the most common. As we saw in previous slides, most removable equipment utilizes a braced understructure. To increase the usable space beneath platforms, moment frames can be used, but typically require special, more expensive details. They're more time-consuming and intricate methods for installation, and they thus usually strategically placed brace frames are used, or platform systems are braced to existing building elements when possible. Note that for lateral load to reach these systems and be transferred safely to the ground, a diaphragm, such as the one shown in Figure 2, must be present. A diaphragm must be relatively rigid in its own plane, so the roof, for example, so that it can effectively accomplish this. For buildings, this is usually, again, the roof or the floor level, and analogous in the demountable system, which is much smaller, is the relatively thick plywood or other surface, could be aluminum or even steel, and then when you lock all those platforms together, you easily get that required amount of stiffness to make a diaphragm. The bottom line is here, clearly it's important to take lateral loads into consideration. And as noted, before planning on creating usable space beneath removable systems, coordinate with a qualified demountable contractor and check local jurisdictional requirements, as they may require specific lateral loads, even though they're not stated explicitly in code. Now, exterior structures will be subject to wind loads. These loads occur both vertically, uplift, and laterally. Recent collapses due to high wind events at outdoor performance facilities have highlighted the need for both design professionals and facility managers to consider plans to mitigate risk to life and property. The most notable of these collapses occurred at the Indiana State Fair in 2011, of which Staging Concepts was not involved in, but you can see that what happened in this image. The collapse of a concert stage occurred as the result of a sudden wind gust. A thunderstorm came through. The stage was heavily damaged. 7 people were killed and 58 injured. Numerous other failures occur every year, with property damage luckily being the primary consequence. You don't hear, they're not high profile, you don't hear about them in the news necessarily like this one. The building code requires permanent structures to be designed for wind loads, but the requirements for temporary structures are not as clear and vary by jurisdiction. Some jurisdictions require temporary structures to be designed just like permanent structures, while others may allow reduced wind loads, or they may require high wind action plans. These are plans that involve a detailed evacuation plan and a team of on-site professionals, meteorological professionals using electronics and other systems to closely monitor the current weather conditions during an event. This can be quite cumbersome and expensive, but that's what some states right now require. In the absence of the clear code requirements, as I'll show you on this next slide here, we recommend that the design professionals, facility managers, and facility owners utilize a risk management analysis. I've highlighted what are, in my opinion, some of the more important considerations here in red boxes. Generally, the team needs to consider the size of the installation and the risk it poses to human life and property damage. In some jurisdictions, the length of time a structure is in use or installed may also dictate the design, how much wind load to use. Solutions ranging from ballasts, some heavy concrete blocks or sandbags, to soil anchors can be effectively utilized as needed to mitigate these risks. But again, consult your local jurisdictional authority on this issue early in the project. In many cases, and I've seen this happen, this becomes an issue upon final inspection by building officials before an event. That's obviously not the time to be addressing any issues, let alone one that may require additional equipment installation, which sometimes is not possible or cost prohibitive at that stage in the project. So moving on to our next topic here, this is really about how safe a system feels to users and how well it meets its intended function. In engineering, we typically refer to these sorts of issues as serviceability issues, and they can be just as important as the structural issues. Deflection describes how much a system is displaced or moved under load. Lateral deflection or sway is caused by sideways forces, as we discussed a little bit previously, and is usually of lesser concern, but should be considered at the very least. Again, that might depend on the jurisdiction. In some high seismic regions, you definitely have to consider that, as we mentioned here at the bottom. Deflection limitations are put in place so that users feel comfortable and adjacent or attached finishes or equipment are not damaged. Most permanent systems like floors have very stringent deflection limitations of around the length of the span, the length of the floor beam divided by 360. L over 360 is how you'll see that reported, so that users feel comfortable and excessive movement does not damage furnishings, finishes, or equipment. These concerns are not as important for most temporary systems, and users expect to feel more movement of a temporary system when compared to permanent installations. They're not as uncomfortable when they know that it's a temporary system. Deflection is often neglected, though, or overlooked because code is not specifically limited for demountable systems, but is nonetheless important and should be considered. Design teams should think about the use of the system, where it is in a building, and how it might feel to the groups using it. A deflection limitation may be appropriate in situations, for example, where large equipment is used, or other applications where users may expect to find consistent behavior between a permanent and a temporary system. Where you might walk across a stage floor that's concrete onto a stage trap that is demountable. A qualified professional should be engaged when considering this, as too strict a limitation could double or even triple material costs. So you definitely want to talk about this. Another serviceability issue relates to specifically to demountable structures, include dynamic behavior and general durability. Dynamic concerns primarily deal with vibrations of floor systems. Vibrations are essentially accelerated movements that occur with occupants and will occur in any system based on the movement of the occupants and the structural properties of the system. More lively activity with more flexible structures may result in user discomfort. Considerations are made so that people will not feel uncomfortable when the system is in use, and various acceleration limits are proposed by standards to prevent that discomfort. And there are cases where vibration issues may result in structural problems. This is especially a concern when specific rhythmic chants are used. This happens at Major League Soccer games. That's what these images are taken from. The frequency of the movement can occasionally match the natural frequency of the system, which will amplify applied forces. These issues should be addressed early in the design stages with the demountable system contractor, again, and efforts to mitigate vibrations after the system practically impossible. It's very expensive. You have to add weights or change the geometry. Durability of system components can also greatly affect their performance. Materials that are appropriate for the environment should be selected, and wear surfaces should have appropriate durability for use. Aluminum or stainless steel is best suited for exterior environments, for example, and walking surfaces should be made of a material that is resistant to scratching and has adequate features to prevent slipping. In addition to that, as we talked about, when you have concentrated loads, you want to make sure you're not denting that surface or punching through it. Those are structural and durability issues. Over time, you can actually, with high point loads, if you have wheels moving across the surface, you can degrade the material enough that it's no longer structurally adequate. And finally, in addition, system fastening and operation devices should be taken into consideration, as multiple uses and potential wearing of components can occur. Demountable system contractors are again the best person to consult early on regarding the system features, setup and strike instructions, training, that sort of thing, to make sure that you're taking that durability into consideration. Okay, now we'll talk a little bit about the safety factors and materials. You understand the loading and the serviceability considerations. It's a nice segue into this topic. Safely engineering structures means that the stress or load induced in structural elements be below the structural capacity of the element. I think that makes some intuitive sense. You can't exceed the strength of the material, basically. Historically, safety factors are used to describe the ratio of the strength of a structural element to the applied stress. And that makes it certain that we're below that capacity. As is noted, higher safety factors are used for more sudden failure modes like fracture that could result in a catastrophic failure, as opposed to yield, which is a slower bending of the material that may not actually cause the structure to fail. Metals are predictable and the properties are easily established. They exhibit a yielding behavior, like we just talked about, a permanent deformation before a failure. They're ductile in most cases. Safety factors prescribed by code are usually in the range of 1.5 to 2. 2 being on the upper end, usually when you do have that fracture of that metal. And most of the materials that we're using are metal. Design teams should also understand and be able to distinguish between testing and engineered design. They occasionally get these things confused with one another. Factors of safety are relevant only to engineer design, not testing. In other words, for all demountable systems, including railing, testing involves applying a discrete load to the system in a laboratory or in the field. Per IBC Chapter 17, testing is usually only suggested or required if the materials in the construction are outside the scope of IBC or the standards therein. Testing should not be used as a substitute for engineering a system, as the factor of safety for testing prescribed by IBC is 2.5, much higher than what's in material standards for most metals, and is technically not allowed if the product can be engineered. So that's the important distinction. If you can engineer it per the standards in IBC that are referenced by IBC, then you really can't do this testing method and get around it. And perhaps more importantly, testing can become very expensive, right? While testing is not required for most demountable equipment, if it's required by the owner or the general contractor or architect for peace of mind, it should be discussed with the design team and written into specifications. The loading requirements we previously discussed and the connection to member sizing is fairly obvious. Larger imposed loads result in larger members to resist them. Material selection is also straightforward. Stronger materials will require smaller sections. Most materials used in demountable design are relatively close in their strength. So aluminum and a high temper aluminum, you can get a lot of different strengths, is similar in strength to your typical steels. Member sizes are therefore not drastically changed much by changing materials, but the geometry of the system is the most significant driver in determining member sizing. So, for example, materials are often selected so that units can be handled safely by two individuals or erected with the use of limited equipment. So for demountable platforms, this means that aluminum is most often used. It's roughly a third of the weight of steel, and many alloys, like we just said, have the same strength property as steel. But the caveat is that it's 3 times as flexible as steel. So that means that for longer spanning demountable systems with higher deflections, if you have a really long aluminum beam, it might be more efficient to use steel. Even if it's more difficult to haul around, it will probably be more efficient than the piece of aluminum that would be the same deflection. Aluminum also requires more specialized labor and processes, including welding, so it may not be as widely available as manufactured steel components. And finally, in exterior conditions, temperature loading that causes expansion and contraction of components should also be considered. Usually, temperature loading can be accommodated with simple expansion joints or with the use of similar materials that expand at the same rate. So it's usually not a big deal. Again, it should be something that you think about, though, at the very least at the beginning of the project to make sure you're not missing something. So thanks for your time, and I'll turn it over to Adam to discuss some current trends and review some case studies.
My name is Adam Copperrood, and we're going to look at Section 4, which is Current Trends. Newly built sports venues are using larger areas for premium and non-traditional type seating areas, such as suites, loge boxes, multi-use concert spaces, and restaurant or bar terraces. Removable equipment is often incorporated into designs of these areas early in the design process, but in established venues, removable equipment provides the flexibility to transform these areas for other uses. The Petco Park VIP seating area, on the right side of your screen, is an example of retrofitting over traditional row seating. Once the row seating is removed, platforms are built over multiple rows of concrete stadia to create VIP areas. The overbuild systems can be designed to match the surrounding finishes of the venue, so they have a permanent look and feel along with the flexibility to be easily removed in the future. This is a popular solution for venues with seating sections that are difficult to sell out. Event-level seating and party decks are also a trendy solution that can incorporate demountable platforming. In most cases, event-level seating needs to be removable to accommodate different events in the facility. These areas can be built in fork-liftable sections with retractable casters to gain maneuverability. Finally, VIP party decks have increased in popularity as teams look to increase their fan experience and in-game viewing options. We know that venues are continually looking to do more with their existing space. The rise of esports is an example of a fast-growing sport that venues are trying to accommodate. Portable platforming provides venues with the flexibility to adjust seating configurations to accommodate a wide range of events. Adjustable scissor lift platforms can be used to transform a space from a flat ballroom floor to a stage extension or into a tiered seating riser within minutes. They reduce the amount of changeover time between events and provide the flexibility that venues are striving for. In performing arts centers, flexible spaces like black box theaters remain popular. These spaces are often designed with demountable seating platforms that can accommodate multiple seating configurations. By all appearances, it looks as though social distancing requirements will be in place for at least the first half of 2021. Most of the trends that we have discussed could also be considered social distancing solutions, as we are reducing seating capacity to create unique VIP spaces. This picture from the UK received a lot of attention on social media last summer, as entertainment venues have been exploring ways to move more events outside. This trend has created an increased demand for outdoor rated portable platforms for seating areas and performance stages.
Hi, my name is Tom Bateman, and I'll take you through Section 5, Case Studies. Now let's look at putting all the pieces together. I'll take you through a few case studies showing demountable equipment applications that illustrate how the components are used and how versatile they are, some of the technical aspects we discussed, and how the project process we discussed can lead to success. The first case study is Midtown Arts, Houston, Texas. There are several different ways platforming can be used to add flexibility to a theater. Platforms can make up an orchestra pit filler or stage trap in a proscenium-style theater. Here in Midtown Arts in Houston, Texas, we have a black box theater that has a multi-configurable seating riser. In this drawing, you see the platforms organized in an arena configuration where there is seating on all sides of the performance space. In the picture on the right, you have those same platforms reorganized to make one large riser in an end stage configuration. There are lots of opportunities to customize and make these risers fit the needs of the space. The next project is Zephyr Stadium, New Orleans, Louisiana. At Zephyr Stadium, we used very similar components but changed the riser materials to be all aluminum to make an ADA infill off of the concourse of this outdoor stadium. This allowed the stadium to add required ADA infill space that is removable and at the same time save time and money from using concrete. We also added the aluminum drink rails from the photo. Next we have Petco Park, San Diego, California. As discussed briefly in previous slides, at Petco Park in San Diego, we used platforming to build a 3-tier VIP riser over the existing 7 tiers of concrete stadia. The riser uses weather-resistant platforms and custom guardrail to provide a permanent look and feel, but has the ability to be removed for an event that requires a larger capacity. Next is Jacksonville State University, Jacksonville, Alabama. Jacksonville State University is a great example of how prefabricated, unitized equipment can be used to save time and money on the renovation of a performance space. Staging Concepts installed steel raker beams that supported our platforms. This created a more intimate seating layout for JSU's basketball arena that is permanent and accelerated their construction schedule. From beginning of design to completion on this project was 5 months. This is a great example of the effective use of collaboration early in the design phase to achieve economic and aesthetic success. Next is SoFi Stadium, Los Angeles, California. Los Angeles' new SoFi Stadium for the Rams and Chargers was an exciting project that we just recently completed. We worked with the architect to come up with a demountable seating solution that would allow them to lay out a wider soccer field for possible World Cup events. The forkliftable seating sections were built to span over suites and have attaching LED scoreboards, field pads, glass rail, and a water runoff system. Next is Bank of California Stadium, Los Angeles, California. For Bank of California Stadium, we built a large demountable seating riser system in the north end zone using what we call the SC Pro seating riser system. This system was built to be in place to seat the supporter fans section during LAFC football games and can be removed for concerts. The system has safe standing rail with integrated seats and was built to be compliant with earthquake loads, and more importantly, for football fan chants that include a lot of jumping. Next is the NCAA Final Four at AT&T Stadium, Dallas, Texas. For several years, we've been working with our partner, the Colonnade Group, and the NCAA to convert the seating in football stadiums to be more intimate for Final Four basketball tournaments. This equipment travels to whichever stadium is hosting the tournament that year, and we help to ensure they have what they need to fit the riser into each unique space with minimal parts and pieces. The basketball court is also elevated on a stage system for enhanced sightlines. This type of installation requires a lot of design work and collaboration with the execution teams, occurs on a tight timeline, and is thus a great example of the versatility and usability of unitized components and how that collaboration and communication with our design team leads to success. Please note our sources for the technical information provided in this presentation. This concludes our presentation on demountable equipment. I hope the information shared on this presentation will help you specify and design demountable systems on your upcoming jobs that are safe, versatile, and aesthetically pleasing.